So now let's look at examples of optics, in particular examples of reflection, refraction, and image formation using mirrors and lenses. First, we'll look at examples of reflection and refraction, and then in the next video, we'll cover the examples of image formation using mirrors and lenses. Consider now the following problem. You have a beam of light. It has wavelength of 490 nanometers and it travels in air from a laser to a photocell in 17 nanoseconds. A slab of glass 0.84 meters thick is placed in the pathway of the light beam in such a way that the beam is incident along the normal to the parallel faces of the slab. It now takes the beam of light 21.2 nanoseconds to travel from the laser to the photocell. So the only difference between the first case and the second case is that in the second case, you have a slab of glass placed in the pathway of the beam of light. Determine the wavelength of light in the glass. You'll recall that in our discussions of index of refraction and light, the wavelength of light changes when the index of refraction changes. That is, when light moves from one material to another, the wavelength of light changes. So let lambda air be the wavelength of light as it travels in air. Lambda air is equal to 490 nanometers or 490 times 10 to the negative 9 meters. We have two cases, initial case and final case. In the initial case, light is only traveling in air. The time initial is given to be 17 nanoseconds or 17 times 10 to the negative 9 seconds. In the final case, the light travels in both air and the slab of glass. The final time is given to be 21.2 nanoseconds or 21.2 times 10 to the negative 9 seconds. Let d glass be the thickness of the slab of glass, 0.84 meters. Now it's clear that the time of travel in the slab of glass is given by T final minus T initial. It's the difference between the time of travel in the initial case and the final case. 4.2 times 10 to the negative 19 seconds. Knowing the time of travel in the glass and the thickness of the glass, we can now calculate the speed of light in glass. V glass is equal to D glass divided by T glass. 0.84 divided by 4.2 times 10 to the negative 9 seconds. We are then able to calculate V glass to be 2 times 10 to the 8 meters per second. And with knowing the speed of light in the glass, we can then calculate the index of refraction of the glass. N glass is equal to C divided by V glass. Speed of light in vacuum divided by speed of light in glass. Now, index of refraction of air is 1 or relatively speaking equal to 1, the same as index of refraction of vacuum, which means that the speed of light in vacuum and the speed of light in air are relatively the same, which also translates that to wavelength of light in air will be the same as wavelength of light in vacuum. So N glass may also be written as lambda air divided by lambda glass. The only unknown is lambda glass, and we are able to calculate lambda glass, the wavelength of light in the slab of glass, to be 326.6667 nanometers. Next, we have example 2. You have a parallel beam of light as shown in the figure, and the beam of light is incident on a prism as shown in the figure. Part of the light is reflected on the right face of the prism, and the other part of the light is reflected on the other face of the prism. Show that the angle theta is twice the angle A. Applying the geometry of bisecting lines and the geometry of triangles, and since light reflects off the faces of the prism, we also apply the law of reflection. And we see the following angles apply. Clearly, angle theta is equal to A over 2 plus A plus A over 2. And that gives us theta is equal to twice the angle A. And so we move on to the next example. Consider the following situation. You have a tank filled up to the top with an unknown liquid. An observer with eye level with the top of the tank. So eye level of the observer is at the top of the tank as shown in the figure. Can just see the opposite corner, bottom corner of the tank, point F. Determine the index of refraction of the unknown liquid inside the metal tank. The dimensions of the metal tank is given in the figure. Let D be the height or the depth of the tank, 0.6 meters, and let capital L be the length of the tank, 1 meter. Now, for point F, or for the opposite bottom corner of the tank to be seen by the observer, light from point F must travel to the opposite corner, opposite top corner of the tank, and then from there, it will travel to the eye of the observer, and point F will then be seen by the observer. So as you can see, light will travel from one medium to another. From the unknown liquid inside the metal tank, light will travel to air, and then light will be seen by the observer. Let the N1, index of refraction N1, be the index of refraction of the unknown liquid, while N2 is the index of refraction of air, which we know to be just equal to 1. Also from the figure, we see that the angle of incidence, the interface being horizontal line, the normal to the interface is the vertical line. The angle of incidence theta 1 is given or is shown in the figure. And from the figure, we see that the angle of refraction, theta 2, is 90 degrees. Now, we can calculate theta 1 using the dimensions of the tank. Trigonometry tells us that tangent theta 1 is just equal to opposite over adjacent. So that's L divided by D. We can calculate theta 1 to be 59.03624,347 degrees. So we now know the angle of incidence theta 1, the angle of refraction theta 2, as well as the index of refraction of air N2. If we now look at the equation for refraction, or if we look at Snell's law, N1 sine theta 1 is equal to N2 sine theta 2. We see that the only unknown is N1, or the index of refraction of the unknown liquid. Isolating N1, we are able to calculate N1 to be 1.1662. And finally, we have the following example. You have a triangle or prism made out of glass. Index of refraction is 1.81. You have a prism ABC. Light is incident on the face AB as shown in the figure. Determine the maximum value that angle phi can have so that the ray of light will totally reflect at the face AC if the prism is immersed in water. The glass prism is immersed in water, so we have two materials or media, the glass prism and water. In terms of index of refraction, we have N1 and N2. Let N1 be the index of refraction of the glass prism, 1.81, and N2 be the index of refraction of water. Now, it's not given by the problem, but we know the index of refraction of water to be 1.33. First, light enters the glass prism, so from water to the glass prism. Since, as shown in the figure, the ray of light is perpendicular to the interface, so it's parallel to the normal line. If you apply Snell's law, the light will simply pass through the interface, no change in the direction of the beam of light. The beam of light will then travel to the glass prism, eventually reaching the interface AC, the face AC of the prism. So here, the medium one will be the glass prism, and the other side of the interface will be water, so medium 2 yung water. Let theta 1 be the angle of incidence, and using our knowledge of geometry, we see that theta 1 plus phi is just equal to 90 degrees. So if we can find theta 1, we can find the angle phi. So first, we apply the Snell's law, the law of refraction rather. N1 sine theta 1 is equal to N2 sine theta 2. Now, total internal reflection happens according to the problem. So, theta 2 will just be equal to 90 degrees, and we are able to calculate theta 1 to be 47.290871 degrees. And knowing theta 1, we can now calculate phi to be 42.7091 degrees. And that's it for now. We'll continue our discussion of optics examples in the next video.